again, in order not to be too abstract, let's go back to this. So I want to give you some explicit examples of such relational observables. Let's just throw the formalism on you, but maybe it's useful to illustrate again. Let's go once more. So suppose the kinematic Hilbert space is just L2 over R times an L2 over R. For simplicity, it could be more complicated, of course. And then G is again the translation group. And we have a constraint, total momentum. Let's call it what? Well, call it R and S. So then we have PR plus PS. That's the total momentum. And well, that's the global translation group generator. And then we're going to choose again as phi of G R. We're just going to pick now again, X R. The position eigenstates as before. I mean, we discussed that before. That this gives you, of course, also even a projection valued measure. And now suppose we want to know what we want to measure QS. So the position of the second particle. So really, what we're looking at is we have. So I have one particle R and I have another particle S, and well, this has a position QS and this has a position QR. And now suppose we want to know what OQS relative to R is. Now the orientations, so here we have this group label G inside. So G is now a translation group valued, so let's call it Y. Why not? So Y is real valued, and so let's just spell out this definition here. So yeah, I hope it's clear here. I always omitted the G there, but the integration is over all of G. So in this case, we're going to integrate over all of R. And so let's call it dx u of x. Then we have y, r, and then we have this qs here. And then we also have a u of x dagger. And u of x is just e to the I x p total. So, I mean, I can factorize this here, of course, this guy. So we have that this gives me x plus y. So plus y or minus y. And then I have a conjugation of qs with e to the IPS, right? So I have e to the IP, oops, x ts qs IP sx. So that's what we have. Okay, I hope I'm not making a sign error now. This is qs plus or minus x. Minus actually. Okay, I'm probably gonna the sign. It's up to sign correct. But if I want to figure out whether it's a plus or a minus, I'll probably take 3 minutes and confuse myself along the way. So. Put a plus minus. And I guess likewise here. I leave that as an exercise for you guys to figure this out. And now, so what did I want to do now? So yeah, well, anyway, I get QS, that's right. Now here, yeah, so this is a product. Yeah, so I mean, here for QS, this here is just going to give me a resolution of the identity for the first part, so that's why I just get QS here. And then I get plus minus dx, and then I have x. It's a bit embarrassing to write plus minus, but I'm probably going to make it worse if I the identity on S. Perfect. So so here we can do a change of integration variable. So we're going to call this here. Let's call this Z. Okay. So then I get this is QS plus minus. I'm probably going to correct the plus minus issue now with the end result because I know what the result should be. So so then you can now go dz, and then I have a z, and so that's that minus plus y z. Yes. So then, okay, you can see that this part with z here. That's okay. So there has to be a minus sign here. So I will be getting QS. So let me delete the plus sign here. This is the plus sign is wrong. Yeah, it must be minus. So I guess this is also a minus. Plus is wrong. Minus is wrong. So we get QS minus QR, and then okay, and then minus Y. So that's the end result. So you can see. So Y is of course it's just a parameter. It's not an operator. So you should think of this times the identity, of course, the last. So, so clearly this is translation invariant. It's just a relative distance between R and S. And it gives me, the interpretation is that this is the position of QS when the particle R is in position Y. And so actually there should be maybe actually, okay. Maybe this is a plus sign here. So this should be, I think there should be a plus here. From what I want to have, basically. I'm sorry for this sign issue, and I think that's the way it should be. But so you can check for yourself. So. Probably going to take 15 minutes to figure out what the sign is, and but you know the main part is anyway the first piece here. It's the relative distance. It's translation invariant, and Y is just it's another parameter. And the definition should be that this measures QS when QR is Y, and so the reason I'm saying that that I want to have a plus here is that. You can see this in terms of gauge fixing. So if I set QR to be Y, this has to cancel the Y here, and then it gives you QS. So that's how you can see this.
When do you say about the algebra A? Do you allow the unbounded operator?
Oh yeah. So I mean that's why I was initially, remember when I wrote A kinematically as AR tensor AS, I left implicit what AR and AS are because it depends on the situation. So here, of course, this is unbounded. So, so if I wanted to include this here, then AR and AS, there would have to be, for instance, the algebras of polynomials and Q and P and so on. That's also an algebra. Of course, I could also say, well, I want to look at bounded operators. Then this is still interesting what I'm doing, but the only thing that I will have to do in the end is I take bounded functions on that. So I can also do that. But that's really one of the reasons why even if I specify what the kinematic Hilbert space is, I leave a bit more wiggle room for what AR and AS are because it depends on the situation at hand. Okay, so that's one example. And now I'm going to do the second example again with clocks, so relational observables with clocks. Or is there any question on this one here? No. Okay. So then now let's do relational dynamics. So suppose we have Hkin is a clock Hilbert space, a system Hilbert space, and then we have a Hamiltonian constraint. So I'm not telling you where it comes from, so some reparametrization invariant action. So it could be a gravitational theory. So suppose we have that the constraint is of this form, so no interaction term. So that the conditions that I imposed initially, that they're true, or the assumptions really. And now we can just look at the definition of that guy there. So at this moment, I'm not going to look at a specific observable Fs. So Fs is just some system observable, doesn't really matter what it is. And now I'm going to call the G label here, I'm going to call tau. So it's a clock reading value, right? So remember these G labels here, they label the orientations of the reference frame. So here it was this Y, so the position. Now for relational dynamics, it's going to I just call it tau because it's a clock reading. And then again, okay, I should say here, so same assumptions on HC as before. So I gave previously an example with clocks. I'm just going to be using that. And so now we have this integration over t, u of t, tau, and then fs, and then u there of t. So this is a relational observable that measures fs when the clock reads tau. So that's kind of this quintessential relational observables that are in the canonical quantum gravity community. Maybe let me try and see if I can so this would be tau plus t, tau plus t. Then I have this t plus so I'm just using that I can factorize u into a clock and system part. The clock part, I'm using, oh sorry, these clock states are the same ones that I defined before, using the energy eigenstates, if you remember. So remember that I showed that they are covariant, those clock states, so I'm just using that covariance here. And then I still have to transform the system observable. So I'm going to be looking this up because otherwise I'm going to make a mistake with signs again. So the reason I'm including this now is it's mostly for Yuki, who was asking about the Young-Has power series, so I'm going to make that explicit. So it's yeah, so we have this. So yeah, now I can do a integration variable relabeling. Okay, let's call this t tilde here. Okay. And since we're integrating all R, I mean, there's no problem here. T tilde c. And then I have, I guess, us t minus tau, fs, us, oops, t minus tau. Yes, and then, so now comes the part for which I need the computer here because I'm not going to remember the the relative signs. So yeah, let me just call it. I'm going to call it T again, whatever was T tilde. And so now I'm just going to write this in terms of a power series here. This last part formally. So you can write it as n equals 0 to infinity I factorial t minus tau n. Then we have a nested commutator of fs plus hs. So that's why I wanted. So is this clear? I mean, I'm just rewriting the conjugation of fs in terms of a power series of nested commutators. So the only thing that I wasn't sure about is the relative sign here. So that's why I needed my computer. But what you see here is, so I write this as a power series. So really, I mean, this here you can expand, of course. So tau is just this evolution parameter, and t is the variable that I'm integrating over. So, you know, this here you can of course expand in powers of this t, right? We'll have various powers of t to the n, and then I have tau times t to the n minus 1 and so on. And this is integrated over in terms of t. So remember, these are the nth moments of the clock variable, right? So here, really, I have the t to the n appearing inside here. Is that clear? So it's these t's with that integral. So
sorry, what do you mean by the commutator with subscript n?
Oh yeah, so I just mean a nested commutator. So I mean, yeah, good that you're asking. So I mean, fs, hs, n minus 1. Yeah, and also with the condition that fs, hs, 0, fs.
You mean another commutator which ss?
Oh, sorry, yeah, no, it's hs. Sorry.
Okay.
Yeah.
Thank you.
Yes. So yes. And so the 0th one is just fs, and so this is what I meant by the nested commutators. And so yeah, anyway, you see that you have the nth moment operators appearing in here, and okay, okay, so. And this is when you have this here, this is a quantization of, let's put a hat over here for the moment. So we have a classical analog, fs, r, tau, c really. I guess it should have been c, I'm sorry, here the terminology I'm using. And then I'm just using n equals 0 to infinity. Okay, I hope I'm not doing something wrong with the sign again. So n's power n factorial. Yeah, no, I think actually it's the other way around when I go classical. Let me write it like this here. And then I go fs, hs, and the nth nested Poisson brackets, where this for Poisson brackets is defined in the same way as this here. So the reason I'm changing the sign here relative to this is that I have this I here. You know, if you follow the Dirac quantization rule, the Poisson bracket is commutator over I. Okay. Now this here is the canonical power series representation of relational observables due to Bianca Dittrich from 2004. So that answers your question. And so here I should say that here in this case, such that T HC, well, this is 1. So this is important here, the classical formulation. So here, the HC is no longer appearing in here from the commutator, but that's the same as here, right? So the HC that is in this way of writing things in the unitary, I've written it in such a way that it doesn't appear anymore explicitly. So it also doesn't appear anymore explicitly in the classical analog. But the importance here is really that in order for this form to be true, I mean, this power series is written in more general ways than what I'm explaining here. But this form is true when the clock is conjugate classically in a Poisson bracket sets to the clock Hamiltonian. Okay, so that's just to answer Yuki's question, at least for this type of relational observables. And then maybe one more thing for ideal clocks. So this here holds for non-ideal clocks also. So for ideal clocks, when tau prime is delta tau minus tau prime, we have something even simpler. It simplifies, and for instance, we can look at O hat Fs relative to C. Let me set tau equals 0 for the simplicity here. So you can work this out. So really, here when I have ideal reference frames, I can basically take, these are orthogonal. I can take this integral and I just throw it into the power series. Okay, and I can replace t by t hat. Okay, so in this sense, I will get e to the minus I t. I write t1 because it's the first moment, but it's of course. Let me just write t, and then I have hs, fs. So e to the plus I hat hs. Yeah. So where t hat is t1. So you see it takes a very simple form for ideal clocks. It's just conjugation of Fs by a unitary, where I'm replacing the usual time parameter t by the operator t, the clock operator t that corresponds to the clock. And of course, because the clock lives on a different Hilbert space, this t and hs, they commute. Right? So that's no problem in writing it this way. So, so this is only true for ideal clocks, but the reason I emphasize this here is also that we will see this in the discussion of cross products. Sorry, I didn't actually say what cross products are, but it's this discussion by Witten and so on about observers and closed universes and so on. So we will see this again probably tomorrow. Now I'm coloring my hands here. So that's for the examples. I thought the pen was closed and I colored my hands. Okay. Yeah. So that's for the example. So I would like to now move on with the dictionary. We're not quite finished yet with the dictionary, and let me try to finish it before the end of this lecture day.
So what's happening for ideal clocks?
Sorry.
What's happening for non-ideal clocks?
Well, for non-ideal ones, this is still true. So this one is true for under all the assumptions that I made.
Well, how about the last spreadsheet?
This one here is not true for non-ideal clocks. Yeah.
How about cross product?
Sorry?
Cross product?
Yeah, cross products are only true. I mean, cross product requires ideal quantum reference frames. So when you go to bounded clocks, you go to subalgebras of cross products. But it's not a cross product itself anymore. Can I wipe this out?
Sorry, would you keep the last one?
This here?
Yeah, here, yes, sure.
I guess that. Okay, so then let's move on. So we have, again, special relativity and the reference frames. And so, so we have now explained what are internally distinguishable configurations of the system. And right, so now we want to come to the quintessential question of internal quantum reference frames, which is jumping into an internal frame perspective. So, so yeah, we need to clarify what that means, because before we can say what it means to change quantum reference frames, we have to, of course, say what it actually means to jump to frame perspective. And so there's two equivalent ways of doing that. And one is relational observables. Remain gauge invariant. So here, okay, gauge invariant in special relativity quotation marks. So really, I mean, in this case, you're just looking at these relational observables. So that's a description. You can view that as a gauge invariant way of describing what how the system looks like relative to the reference frame. And there exists another one, which is basically aligning the external plus internal reference frames. So really you can view this as a gauge fixing. And this really hinges also on the equivalence of gauge fixing and gauge invariant descriptions. And so here, for example, we can set E mu A to be delta A mu. Right. So this means we're actually aligning the internal and the external frame. Because this year's, so we had our X and our T. And I think I had it in red before. The 0 and so on. I mean, there's of course more than two directions in general. But this here is subject to these gauge transformations, lambda mu nu. So I can act. I can act with a transformation like this on the description. So in this case, you can think of it, of course, as changing the background gauge to align it with the internal frame. So that's why I'm calling it aligning. And really what you're doing is you're going to a description. So you're changing it to a description where they're fully aligned. Sorry, E0 and E1. And So that's what this here means. So I'm now gauge fixing, in quotation marks, that the tetrad is in the identity configuration. So this is the identity matrix here. So it's the identity element of the group. So it's in the origin of the group if you want. If I treat these lambda mu as gauge transformations, then I'm allowed to make that gauge choice. It clearly will completely break the gauge transformations. And then, I could have picked any other element of SO3, of course. But then it's also clear, so this here is, let's call this SA. I think I called it SA before. This is, of course, gauge invariant, or external frame invariant. But now you can evaluate SA in this gauge. And then, of course, I'll just have that SA corresponds to S mu in this case. Right? So I'm writing in this form. I hope it's clear what I mean by this. By this identification, the zero direction of the internal and the external frame coincide. X, Y, Z also coincide. So, so clearly the gauge invariant description agrees with the gauge fixed one. So that's why they're equivalent. So now we want to do the same thing, and is that clear so far? So again, of course, I could have gauge fixed this to any other element. So now we want to do this. So in both cases, clearly I'm describing S relative to the frame. And now I can do the same thing in quantum theory. I also have two ways of doing this. So again, the first is relational observables. So what I had already explained to you. So you just evaluate those relational observables. So we have, so we can say we're looking at S relative to R, fits here. And really what this is basically the algebra generated by these relational observables. I'm putting now this twiddle here because I'm talking about the relational observables evaluated on the physical Hilbert space. So from these three O's that I was describing at some point, it's the last one. So, and then Fs, AS. So you can think about it this way. When I write it as a set, but you can think of it as the algebra generated by this. So this clearly describes in a gauge invariant way the system S relative to the reference frame. And now we can also do an alignment of external and internal frames also in the quantum theory. All right, RFs because the external frame is not modeled as a quantum reference frame. So we view this as a gauge fixing. Well, this is literally a gauge fixing. Well, if the symmetry is actually and so what's the analog of this? So the analog of this would be fixing the orientation of the quantum reference frame to be the identity element of the group. So it will be, I'm going to call it R of E, put a subscript R, so these are different R's. And we're going to take that as a map from the perspective loop to a Hilbert space into a Hilbert space that we can call S relative to R. What that space is, this will become clear tomorrow, not today. I don't think I'll get to that. But it's just a gauge fixed Hilbert space. Okay. And R E is just defined to be phi of E R tensor identity of S. So if you're familiar with the Page-Wooders formalism, this is a generalization of the Page-Wooders formalism to general groups. So in the Page-Wooders formalism, you condition on the framework, on a clock reading, and then you get a Hilbert space that is only there for the system, and you get a Schrödinger evolution. So this here really is a generalization to general unidimensional groups. And now, crucially, so I think I can wipe this out now. Yeah, I think I still have SR, refs here. And the crux is, so this is not completely obvious from what I'm going to tell you now. This is unitary. So it's an invertible map. It's unitary between the perspective neutral Hilbert space and this gauge fixed Hilbert space, the image of it. And intuitively, why? So intuition is just a gauge fixing. So there's no physical information. So that's the intuition why it is unitary. It's just a gauge fixing. You know, the quantum reference frame is supposed to absorb all the redundancy in the system. I'm using the quantum reference frame states to gauge fix, so to fix the redundancy. But that's all I'm doing. So I'm getting rid of the redundancy in the description of gauge invariant data. So when we say redundancy in the description of gauge invariant data, what we mean is, of course, gauge invariant data is described typically in terms of kinematical data. So in terms of R and S degrees of freedom, but in terms of composite degrees of freedom. But the amount of gauge invariant data is not fully worth the amount I have in R and S individually. It's composites, right? And I can fix the redundancy by fixing the reference frame. Well, it's just a gauge fixing. And so it is actually an invertible map. So I will explain that. Is it? Okay, 22.5, probably tomorrow. So, and for this, in fact, to be feasible, that you can do a gauge fixing, so that mimics what happens in special relativity. That's, in some sense, also the main reason why we're going to this perspective neutral Hilbert space, where we're taking this radical point of view of going to fully gauge invariant description. But at the end of the day, you can view these R maps, these reduction maps, so we call them reduction maps. They're just gauge fixings. That's like jumping into the frame perspective. Once you do this gauge fixing, the remainder describes only the system, and in the same sense in which you can view that when you make this alignment of external and internal frame in special relativity, you're describing, when you write that in the background coordinate system, your S, that it's the physical description relative to the internal frame, because I've aligned the external and internal frame. In the same way, I can interpret the image of this map as being a description of S relative to that reference frame. Good, yeah, so that's unitary. Yeah, so then maybe we can, are there any questions on this? And because these are gauge fixings, that's ultimately also a reason why the quantum reference frame transformations are going to be unitary in the end. So I was thinking maybe give an example of Page-Wooders. 20 minutes. Why not? It's quick. So we're going to go back to example 2. So we had now this example of HC plus HS. Same assumptions as before. Okay, yeah, one thing that I wanted to say here is generalization. I should probably say that, generalization of so-called page-Wooders formalism. And what I'm going to describe is the standard page-Wooders formalism. So the analog now is we call one thing that I forgot is, I mean, here, just an analogy to special relativity, I've set this to the identity element. Of course, I can put any G in G there. It's just a different gauge fixing. Okay. So for simplicity, I've set it to E so that you can exactly compare it to special relativity, but also in special relativity, I could also put any lambda mu in SO31. And here, I can also put any. It works in the same way. So, and here, in the page-Wooders formalism, so I'm going to explicitly keep the general tau. So it doesn't have to be 0, it could be whatever. And, well, we're just going to have that this is tau C cancel the identity on the system. So again, the clock stays as before. And now we're going to define a system state as being the image of this acting on some. So this here is a round bracket. Okay, so this is a round bracket. So psi elements HPN, the respective neutral limit space. So it's just the conditioning of that state, so I can just define it in this way. And now let's have a look. So we have, we can look at ID tau, psi S tau. So what I'm going to show is that it obeys the Schrödinger equation. So, so I have ID tau, and then I can have tau prime. So I'm now making use of the covariance of the minus tau prime, HC, and then I have some round brackets. Is that clear? So here I'm just using the covariance of the clock state. So here, in this state here, I have RC of tau. So I have this guy inside, and I'm just rewriting tau as tau prime times this here. Okay, so this here is just, so that's what I'm doing. And now we can differentiate this. So I'm going to get down, so I'm differentiating with respect to tau. So I get down an HC, so there's an II, so there's a minus HC, so I'll have a tau prime minus HC, and then e to the I tau minus tau prime HC psi, round bracket. And now I can take the tau prime, I can take this guy here again, and I can put it back here. Okay, so it's a so this is tau. Then I have minus HC, so minus HC psi. Is that clear? But now you should recall that because of this here, I have that HC plus HS psi is 0. So that means minus HC acting on psi is equal to HS. So this is tau HS psi, but then this here is only clock state, this acts on the system, so this is HS psi S of tau. Can you read this? Okay, maybe I need to. Well,
It's okay.
Anyway, I mean, so the end result is hs psi s of tau. So you see that the state obeys the Schrödinger equation. So is that clear? So I'm using the invariance of the perspective neutral states. They obey the constraints, and I use the covariance of the clock, so that's all I'm doing. So then you see that, you know, so this is the standard page Woods. But I think it's from 1983 or something like this. So then, okay, they didn't use the language of quantum reference frames. So it was us incorporating this in the language of quantum reference frames. So identifying these clocks as temporal quantum reference frames. But what you see is then, so it was actually also us showing that these reduction maps are unitary, and the gauge fixing that was actually surprisingly not realized before, despite 35 years of time having passed between these initial works and us. But it's really important that these are actually unitary. So when you look at these maps, it doesn't look like anything like a unitary because I'm throwing away information. But the crux is, of course, that so if I did this operation on a kinematic Hilbert space, very clearly it's not going to be unitary because I'm throwing away information. It's only unitary when you act on the perspective neutral Hilbert space. Because this perspective neutral Hilbert space, as a gauge invariant Hilbert space, has redundancy in it, and redundancy again in terms of the description, in terms of non-invariant data. And all I'm doing is I'm throwing away that redundancy. And so this tells you in particular, and this I will describe a bit more tomorrow, so you have a unitary relation between this gauge fixed theory and the gauge invariant theory. So this is again this kind of equivalence here. And that, for instance, showed that different notions of relational dynamics that are considered in different communities. So Paige Wooders was mostly in the quantum information and quantum foundations community. These relational observables, that's more canonical quantum gravity or also in high energy physics. So what this showed our work was that there's an equivalence between them. It's unitary equivalent. Okay. Anything else I want to say on this? Okay. So I think what I would still like to do is now, in some sense, the final part of this comparison, which is frame transformations. So maybe I can do it in 10 minutes. But then at least in terms of the comparison of the frameworks we're done today, which is maybe good. And then some of the technical details that are behind this perspective neutral framework where I've glossed over some things, I'll try to explain that too. Can I wipe this out here? I will just, well, actually, okay, maybe I don't wipe this out yet because I will first do special activity. So, and now, again, there's going to be two equivalent ways of doing so. So, there's two equivalent ways of jumping into frame perspective, so there should be also two equivalent ways of changing frame perspective. And the first, so we described the gauge invariant version of jumping to frame perspective just by using relational observables. And what we can do is, so we have SA, and SA is, so let me highlight here first the gauge invariant, well, here quotation marks, gauge invariant way. So that's what we're going to do now. So as A, we had as E mu, A, S mu. Now we can make use of write this as E mu, E mu, A, S mu, right? So it's somewhat trivial rewriting. But this is useful because now we can recall that the, oh, actually I forgot to say that we have to introduce, of course, a second frame to the game. Otherwise it's a bit uninteresting. So, so maybe let me first do a new drawing here. So X and T. And so, so now this was our E so this is our first frame. And then the drawing is not the prettiest, but I hope you get the idea. So now we're going to have another one that's called E tilde or something. EU, we're all E tilde 1, 2. So we have 2 frames. And now we can make use of the fact that these frames are orthogonal, so we can rewrite this here. So eta mu we can write in terms of E tilde. So we can write this as E mu A E A mu. Oh, sorry, tilde, of course. Maybe let me just write it in color so maybe it becomes a little clearer. You don't have to correct this, but I'm just going to do it. So this is a mu. So E tilde mu, what's it called? We call it B prime. E tilde B prime. What do we here? And I have my E to A. I have my S U. So, and we're going to write this here as red. So this is SA. So now clearly, if you look at this here, I have this contraction here. So this is going to be the relation observable describing the system in form velocity relative to the second frame. And then I have this here contracting with a space-time index. And I'm going to write this as, well, what am I going to write it as? So lambda B prime, well, it's not, yeah, B prime A. And this makes sense what I'm doing now. This, so that's S. I'm doing B prime. Is that clear? Maybe I'll add the tilde here. This is just E prime. This is the relation observable. Sorry, that's a tilde. Relation observable of S relative to. I'm going to write it R2, second frame. And then this first one here. So there's a reason why I write a lambda there. So it has 2 different frame indices, as B prime and A. So this here is just, which ones do I have now? It's, let's write this A, E tilde, B prime. And so what is this here? It's also a relation observable. This is the relation observable describing describing the 2 frames relative to one another. So R1, R2 relative to one another. So here, contracted space-time indices. So in that sense, it's gauge invariant. And I'm dressing the second frame with the first, or I'm dressing the first frame with the second. So I'm actually describing the one frame relative to another. And now recall that this is Lorentz group valued. This is also Lorentz group valued, so the contraction is also Lorentz group valued. That's why I'm writing it as a number. So, so this is valued in SO31. And so it is really it encodes. So it's a Lorentz group transformation by an amount where the amount is given by the relation between the two frames. So that is, I can view the, here it's the old relational observable. I can view it as the new relational observable relative to the same system described relative to the second frame, and I have to transform it by a Lorentz transformation that is given by the relation between the two frames. And everything is gauge invariant here. So if I look at this relationship here, so that's the key relation. There's no space-time index there. Frame covariance, but gauge invariance. I should say internal frame covariance and I put it again in quotation marks, and gauge invariance. So it's no open space-time index. Am I already out of time? I'm already out of time, right? So, okay, so let me maybe just briefly write this in a so you can. I'm going to write it in the following way. So you write this as addressing E mu A tilde mu B prime. And then you get here SA. Here I get S tilde B prime. Then the reference frame transformation is just this lambda B prime. So that's what we have. So we recover at this gauge invariant level standard Lorentz transformations. Now, so I should give you, of course, now the quantum analog of this. This will take me probably too much time. So if you're okay with it, can I, the second way of doing it, the gauge-induced one, because that's much quicker on the quantum side. Or should we stop here? So basically, I think sorry that I'm already reaching the maximum time. I mean, of course, if you have to go, you can go. But it would be, in some sense, somewhat more complete if I tell you what the option B is. The special relativity, because the translation of that into the quantum theory is very quick. The translation of A into the quantum theory is not so quick. So I will, basically, the counterpart of this here I will do tomorrow. But again, if you have to go, please, I don't want to hold you off. Okay? So that's why I'm going to first continue here on this side. Okay, so now we're still at the level of frame changes. And I'm just going to tell you very quickly what it is. So it is, now instead of, here we have a non-invariant one, this here means I'm dressing it in two different ways, and the two different dressings are related. Now I'm going to take a slightly dual way where I'm taking already, so here what is happening, I'm actually changing relational observable. Right? I'm describing the same system, but relative to different frames. These are distinct relational observables. I'm changing relational observable. Now I'm going to take one and the same relational observable, and I'm just going to gauge fix it in two different ways. So here, so this is gauge fixing. So here I'm going to set E mu A to be delta mu A, so that's the same gauge fixing as before. And because SA was already dressed with respect to the same frame, here I will just get basically S mu. So that was the thing that we did before. Now, here on the other side, I'm going to do now E tilde nu E prime, and I'm going to set this one to. So, and in general, this is going to be a different gauge fixing, because E tilde and E, they will not be aligned in general. So, so here I'm aligning the background frame with the first internal frame, here I'm aligning with the second one. So in general, it's a different gauge fixing. Okay, I mean, all this will do is that, so here, of course, SA, I mean, if we remember what SA is, so it's E mu A S mu. But then remember that this is the Lorentz group. This is Lorentz group valued, and when you look at this Lorentz transformation here, when I gauge fix it, this here just this one becomes the delta. So it means actually the second frame orientation is this Lorentz group transformation. So it's a yeah, I mean. So really, what do we describe it? B prime A, and then yes, and then S B prime tilde. So this is now the one that's naturally appearing in this perspective here when I gauge fix it, because that's the one that's dressed with respect to this guy. And this here, that's the Lorentz transformation that corresponds to this guy here. So this will look as follows, which is a mu nu, and then S mu here in this way. Okay. So this is the S mu in this frame perspective, and there's a Lorentz transformation. And so then you see again, okay, there's a lambda mu nu, there's a Lorentz transformation between them, it's clear. I choose here one background Lorentz frame, I choose another background Lorentz frame, and they're related by a Lorentz transformation. And this Lorentz transformation is again given by the relation between the two reference frames, between the two internal frames. So in that sense here, it has a matrix, it has different indices, but it's the same object as another. So in that sense, they're again equivalent. Okay. So, so this is a frame relational gauge transformation. So internal frame relational gauge transformation. So this is the thing that we can very quickly generalize to quantum reference frames. That's in any case also the one that is mostly discussed in the literature, the gauge-induced ones. So, so quantum reference frames. So here, again, here are Fs. So A tomorrow. And this one here, I'm going to show it first at the Hilbert space level. So we have, for instance, our, let me write it R1 of E. So that's, oh, okay. I also need to introduce a second quantum reference frame, of course. So I should tell you that. So we have the kinematical Hilbert space is now HR1, HR2, tensor HS. So you can think about it as an R1, R2, and a system S if it's like a three-particle example or something like this. And I told you this is unitary, so this goes to HS. Well, okay. In this case, the system relative to the first frame is R2 and S. Okay. So it will be R2, oops, 2 and S relative to R1. And here I have I can, for example, do it again like here, so this is the analog. I'm setting the internal frame to be the identity element, so I'm going to do the same here. So I do the reduction map with respect to the second frame. So it's the same reduction map that I've written down at some point earlier. So I'm conditioning on the frame, reference frame orientation to be the identity in both cases. And that'll give me now a description of the system. So always the complement of the frame. So if I go to the second perspective, I'll describe R1 and S relative to the second frame. So again, I wiped it all out. But basically, when you do it in page orders, then what I call the system, that's this state that evolves in the Schrödinger evolution. That's the frame perspective state. The system may contain a second clock, and then you could do the same exercise relative to the second clock. Right? So there's no reason why the first or the second clock is preferred. And the crux is that this is a unitary map, and then it's also a unitary map. So I can actually define what it means to go from this description to that one. So we can call that R1 to R2. And we can just define that to be R2 of E concatenated with the inverse of the first. So you see it really has it's a quantum coordinate transformation. And so, so here we need to remember that this is unitary. So it's a gauge fixing just like here. Nothing else. And I haven't told you what the inverse is. So let me just write that briefly here. So the inverse happens to be given by pi pn. You reinsert the frame element, and you have an identity on everything else. So it's giving you. So this is something that I will show tomorrow, hopefully. So basically, but intuitively you can understand why that's happening. So when I condition on this guy, I'm removing the frame. It's a gauge fixing. Now I'm reinstating the frame in the same configuration that it was in before, and I'm going to average, because this is a group average. So I have a gauge fix description, and I'm going to average over the gauge group, so it becomes gauge invariant again. So that's the intuition behind it, and it turns out that that's the inverse. So then you can just look at what this does here. So you have really in a somewhat sloppy way. This is going to be phi e R2, phi pn, phi e, but now R1 here. So there's a 1, there's a 2. So it's in some sense it's not really a matrix element because it's kind of value at different Hilbert spaces. Then you remember that pi pn, I'm just going to recall what it is. So it's dg and then u of g. Okay. So we're going to make use of this. So so we're going to be translating this guy here by g. Okay, so we'll have phi of g 1. Then this guy will be translated by g inverse because it comes with a bra. Okay. So this one will be phi of g inverse 2, and then I still have a us of g. So okay, what I didn't say is that we're also going to be assuming that the group G has a tensor product representation across all 3 factors. So that means in particular that there's a US of G in there, but this is not impacted by the bra on R2 and the ket on R1. So it's going to be, nothing happens to it, the integral. Anyway, that's the reference frame transformation. And so, so this is basically where I want to end up. But so these are what the reference frame transformations. They're unitary because these maps are unitary, so I'm just inverting unitaries. And you can really think of them as quantum coordinate changes. So this here is a literal coordinate change of background coordinates here in special relativity, and that's really a quantum analog of it. And so now you can also understand why this Hilbert space in the end is called perspective neutral, or why this whole framework is called perspective neutral. Because this Hilbert space, so you start out with a kinematical description containing all possible choices of quantum reference frames. They don't necessarily have to come as individual tensor factors. They may be non-locally distributed in this, so you may have to refactorize your kinematical Hilbert space, but there's going to be a continuum of choices of quantum reference frames in general in the kinematical Hilbert space. You go to the gauge invariant Hilbert space, the physical Hilbert space associated with it, and it corresponds, it encodes the information about every possible internal quantum reference frame. For each one of them, I can define this, and I can define a unitary map. And the thing is, so you can view the perspective neutral Hilbert space as a description of the physics before I've chosen an internal reference frame relative to which I describe the internal data. Then I can choose a reference frame, I jump into the perspective, and I can go to any other one. And really, it really is like a coordinate transformation. It has the same compositional structure as coordinate change on a manifold. And really, whenever you go from one perspective to the other, you're always going via the perspective neutral Hilbert space. Just like in a space-time, when you do a coordinate transformation, the manifold is your linking structure. So the manifold is the linking structure between all of these possible coordinates descriptions of a neighborhood. The role of the manifold is basically played by the perspective neutral Hilbert space. The perspective neutral Hilbert space is the linking structure of all internal quantum reference frame perspectives. So that's hence the name of the approach. So so I could do the same. So here I've done this for states. Tomorrow I'll do this also for observables, and then you will see that you get the same kind of structure like here. So here you see, if I take the observable relative to the first frame and I gauge fix relative to the first frame, it looks simple. And I take this observable and gauge fix it with respect to the second frame, it looks a little bit more complicated with this lambda mu there. In particular, this is a composite observable. So this one here is only the system relative to the frame. There's no second frame involved. But then remember that this here really is the first frame relative to the second frame. So this is actually an observable that is compositional relative to the second. It contains the system and the first frame. Okay? And you will see that the exact same thing happens in with quantum reference frames. So if I use these formulations here, I do it for states. But, with relational observables, I can conjugate them by this V map, and I'll see that the same thing happens. So in that sense, you can really see that this perspective neutral framework really mimics these covariance structures underlying special relativity with internal reference frames. It's really abstractly, it's basically the same thing. So yeah, I'm 50 minutes over, so there's a few gaps, but of what I still need to do tomorrow to complete this picture, but at least I think that's a good endpoint for today, that you can see, okay, maybe there's something to the story, but really works there's a nice dictionary between the two. Okay. Any questions?
So if not, then let's thanks Philipp.